At the end of last lecture, we mentioned this linear differential equations. And very often we omit this differential, just say linear equations. If it's in the context of differential equation, it means linear differential equations. The equation is of the following form. So why it's called linear? So this P and Q can be nonlinear, can be sine or exponential. So why is linear? Is linear on the unknown y and y prime? Linear. In this way, we call it linear differential equation. To solve this, as we have seen last time, we want to apply the fundamental theorem of calculus. Okay, that's what we do when we do the integral. We want to apply the fundamental theorem of calculus. Sometimes it's not that straightforward. We have to do some changes to make this the derivative. To make the derivative, we will introduce a term called the integrating factor. A factor that facilitates this fundamental theorem of calculus. Okay, so what is this integrating factor? It's the exponential of an antiderivative or indefinite integral of this function p. We just need one of them. With this is what happens if we multiply all of them with this integrating factor. Now the difference is this is the derivative of the product. So that's why we construct the integrating factor in this way. In this way, if we apply the product rule, y derivative is the first one, and the derivative of I, because it's exponential, we'll apply the chain rule. So I and derivative of the exponent give us a px. Now our differential equation looks like this. So we can apply the fundamental theorem of calculus because it's the derivative. Okay, so you can see how we solve different equations. We want to convert them to integral problems. So previously, last time, we have this method of separation variables. We split this into two integral problems, from different equation problems to integral problems. Okay. Okay, so that's the method. Let's put this into practice. Let's try to solve this differential equation. For this one, let's match with the formula. That's the formula. This is the problem. If we want to match the formula with the problem, okay, Zichen, what is the px? -1. So it's the coefficient of y. So first, this is y derivative y is a linear differential equation. Okay, so first, type linear differential equation. Second, we say that px is -1. Now, what's the integrating factor? How do we construct this? So we want to use this formula. Using this formula, we have a p, we need one antiderivative. -1 dx. Okay, Sakina, what's the integral of -1? Yes, okay. E to the -x. Normally, we will have plus c. Here, we only need one integrating factor, so we can drop this c. Okay, now we will multiply both sides with this factor. See what we get. Okay, we will compare these two differential equations. We multiply both sides with this factor. It's the same equation. The difference is this left-hand side is the derivative of the product. Okay, let's verify. This is the derivative. If we apply the product rule, it's the derivative of the second, derivative of the first chain rule. And this, by the previous equation, is 1. Okay, Sophia, now we have the derivative is 1. What can you see about this unknown function?
It's x.
Okay, this implies will be the integral of 1 dx is x. And don't forget the integration constant c. Because we are finding a solution now. Okay, Elisa, how do we find y? Unmute yourself, Elisa.
X. Wait.
So we have the product is x plus c.
Divided by e to the negative x.
Okay, so we will divide both sides by e to the negative x It's the same as multiplying to x. So this is the solution of the differential equation. So how we solve it? How we solve it? We use this integrating factor to make this side, the unknown part, the derivative of something. If we can make it the derivative of something, we can apply the fundamental theorem of calculus. Okay, let's try another one. We want to apply the fundamental theorem of calculus. Is this the derivative of something? Is this something the derivative? Okay, and both of you, what's your answer? Sophia and Elisa. Okay, so for this one, let's check. X, Y derivative. Okay, Sakina, how do you find this derivative? We apply product rule. It's product rule X, Y derivative. X derivative is just 1. And this is what we had over there. So this will be 3x squared. Now the derivative is over there. So we can see xy derivative plus y. So that's exactly what we have over there. So whenever we can convert this part to a derivative, then we can apply the fundamental theorem. So previously, we have to multiply a factor to make it the derivative of something. This time, we observe it is the product, the derivative of the product. So we can apply the fundamental theorem. So here, this is the fundamental theorem of calculus. Again, apply the fundamental theorem of calculus. If we know the derivative, then the function will be the integral. And this time it's easy. I shouldn't proceed too early. Let me move this. C comes after the integration. Then we divide both sides by x. Okay, so we get the solution. So how to solve this linear differential equation? We want to do whatever we are allowed to make this a derivative. Then we can apply the fundamental theorem. Okay, so this is about this differential equation. Next, we move to something maybe more exciting. got this parametric curve. I think you have seen this before in pre-calculus. So Sakina, have you seen this before? Parametric equation, parametric curves. Okay. So we'll give a quick review of this. The definition of this is a generalization of the curve graph of functions. We start with this is the function. The graph is a curve. But not all curves are graphs. The simplest example is a circle. Okay. This is a curve, but it's not the graph of any function. Sophia, can you tell me why? There's no function. Yes.
Coordinate plane.
What's that? Try that again.
There's no coordinate plane.
No coordinate plane. Okay, I'm not sure if I understand it. If I add, does this help?
There's no scale.
1, 1, 0. So why
No.
we cannot write this as the graph of some function? So, 1 point. Okay, so for a curve to be a graph of some function, have this vertical line test. Every vertical line can intersect the curve at the most 1 point. In this case, it can be written as a function. In our case, if we draw this line, vertical line, it intersects at 2 points. So this curve fails the vertical line test. Of any function, because it's a fail. Okay, so this parametric equations allow us to study more general curves, parametric equations. As an example, if we study this circle, a parametric equation for this will be and we can check this trace the circle, because if we sum the square of x square of y, cosine square plus y square equals 1. And as t moves from 0 to pi, we go around the whole circle. This gives us parameterization of the circle. Okay. Now, let me give you another parameterization. What's the difference? One, two. Elisa, what's the difference between these two parameterizations of the same curve? This one, when t increases, cosine first decrease. X decrease, Y increase, so we move in this direction. Second one, we switch X and Y. We start from here, we go around the clockwise direction. Okay. Another equation. Okay, the second one is a change of the previous parameterization. We change from sine t to sine 2t. Let's guess how the curve changes. Okay, Zichen, what would you say? For this one, we know it's a circle. What about this one? Guess. Oval. Okay, okay. And you? Huh? Okay, okay. Keep that in your mind, and we will compare with our results and see if it's accurate. And Sophia, what do you see?
Ellipse.
Okay, and Elisa, what do you see?
Oval.
Okay, okay, okay. Let's try. Let's see what happens. Okay, so for this, let's first compute some points. So if t zero pi over 4 pi over 2, 3 pi over 4. Okay, first half. Let's complete the table. It's the first column, cosine t. Cosine 0, what's this? Pi over 4. Okay. Pi over 2. And next one, 3 pi over 4. Pi. It's a sine 2t. 0 pi over 4. So sine pi over 2 times this. So it's a sine pi over 1. 2 pi over 2, sorry, sine 0. 3 pi over 4. So 2 times. So if we multiply this by 2, there will be 3 pi over 2. 3 pi over 2 is in this direction, -1. Okay. Okay, this is 2 pi 0. Okay, let's first get these points, see where they are. Is this where we wanted them to be? Okay, so let's mark some. 1, 1. Okay, so first point, t is 0, x is 1, y is 0, x is 1, y. Okay, same. We start from here. Second point, x is sine. So script 0.7, so not over there. Do you agree? These 2 points? First one, this. Second one over there. So x is square root over 2, a little bit less than 1. And y is 1. Okay, the third point, where is it? Origin, okay. Sakina, fourth point. Yes. Okay, yes, so it's the opposite of this point. And Sophia, last point.
Just -1, 0. It's just,
So over there.
yeah, there.
Okay, now I'm going to trace this point. So from 1 to 0 to the power 4, x decrease, y increase. Okay, Zichen, and back to work. So from this point, x decrease, y increase. So how do we change from 1 to 2? X decrease, y increase. So we will move in this way. Okay, x decrease, we go to the left, y increase, we go to the up. Okay, Elisa, what's next? From power 4 to power 2.
It goes to 0.
So we fall back to the origin. Okay, next, from power 2 to 3 power 4. Go down to the third quadrant point. Okay. And the Sakina, last segment, from 3 power 4 to pi. Okay, go up to this point. Okay, so we haven't finished. Is this what you expected at the beginning, Sakina? No, okay. And Sophia, I see the difference. It's not an ellipse. Now let's
No.
continue. Continue the remaining, but let's finish this plot. The next point, so 5 pi over 4. I said 5, but I wrote 3. T x cosine t sine 2t. 5 pi over 4. 3 pi over 2. 7 pi over 4. 2 pi. Okay, Sophia, find cosine t for these parameters. Cosine 5 pi over 4.
That is square root 2. Wait, no, that's negative square root 2 over 2.
3 pi over 2.
That is 0.
7 pi over 4.
That is square root 2 over 2.
2 pi.
Negative 1.
Cosine 2.
No, 1.
Okay. And Elisa, sine 2t.
Um, 0.
So if it's pi, then we have 2 pi, sine 2 pi is 0. 5 pi over 4, so sine 5 pi over 4. So over 2. 5 pi over 2 is over there.
1.
Okay, now we get 1.
Um,
Also times 2, we get 3 pi. So sine 3 pi. So 3 pi. So pi, 2 pi, 3 pi over there. Sine 3 pi,
0.
0. Okay, again multiply by 2, 7 pi over 2. Sine 7 pi over 2.
Um, 0. Wait, no.
So sine 7 pi over 2.
-1.
Okay. So maybe some calculation. So sine 7 pi over 2. This is sine 2 pi plus 3 pi over 2. Sine 3 pi over 2. So what's this? 3 pi over 2 is going downwards, so it will be negative 1. Negative 1, last one is 0. Who is next? Maybe, okay, so maybe Sophia. Now we move. Where is this point? X negative square root over 2, y is 1. Which quadrant?
Second.
Second, okay. It'll be somewhere over here. Next one is easy, the origin, I skip this. And Elisa, this point. Which quadrant is it? X positive, Y negative. Okay, fourth quadrant. So it will be somewhere over here. And we're back to 1, 0. Okay, so we label 3, 4, 5, 6, 7, 8, 9, 9 points. Now we connect this from 5 to 6, 6 to 7, 7 to 8, 8 to 9. Okay, so we move this way, this way. Okay, you can see a small change of the formula. I changed from sine t to sine 2t. You see how the curve changes, completely different from the previous one. Now you can guess what happens if I change this to 3t. If I change this to cosine 2t sine 3t, you have a variety of curves. They are all different. Maybe so I will ask you to if I can show this. Okay, this website is called Wolfram. Do you know that website?
Yeah.
Okay. Okay. Let me stop sharing this. I share my screen. I'm going to stop share and share my screen. Okay, let me open this. Easy to share. Do I have this option? Just content only. Document. If it's screen, okay. Let's just go with the screen. Then something will be small. If I go share a certain topic, it will be large. Okay, so this is what I over there. Let's see a few examples. Okay. Okay, so plot. Cosine 2t sine 3t from 0 to 2 pi. I'm not sure if you can understand. Let's try. Okay, so this is the plot. It's go over this, then go back this. Okay. Okay. Then give me another pair of integers. I have 2, 3. What do you want? 6, 7 would happen. 6, 7 t. See what this is? Oh, it's not bad. Sakina, you give me another one. Oh, you want something different? I can give you a pair. Maybe cosine, both are sine. What happens? If both are sine, see what happens. I'm not sure. I haven't tried before. Oh, okay, it's not bad. So, so this is a very okay. Sophia and Lisa, can you see my screen?
Yeah.
Okay, you can see. So this parametric equations, a small change of this give you very different curves. So sine, cosine, if you play with it, you get make it more interesting. I'm going with sine 60 as a product. Sine 60. Well, let's see. I'm not sure what we get, but let's see. Okay. Uh-huh. So now this is the product. So the first one, sine 60, I multiply by how to make it more interesting. X t plus sine 60 t minus sine 60. I'm not sure what this is. 60. Okay, so some oscillates. Okay, so there's some demonstration. Let me stop this. Back to our notes. Very useful website. So can find all kinds of information over there. Okay. Okay, parametric curves. Next, we will have this calculus with the parametric curves. first one is very straightforward. The slope. If we have a function, like the graph of a function, I pick a point. Let's make it a little bit over there. Okay, Zichen, now tell me what the slope is for the graph at x equals a. Use the formula. Use this formula, not a number. What's the formula for the slope? It's clear note. Okay. So, okay, maybe I should let's have formula. Okay, so it's not well defined. So what we do is, if we draw a tangent line,
Wait, is the limit as h goes to 0?
okay,
Wait,
okay, so we draw a tangent line. What's the slope of this line using this function?
the limit as h goes to 0
Uh-huh.
of
And
h
that,
minus f of a over h.
okay, so what's that term?
The derivative?
Okay, so that's the derivative. Remember this? No? So that's the geometric meaning of the derivative. It's the slope of the tangent line of the graph at a given point. So why is that? Let's record. What's the slope? Slope. Approximate. Now if we take a limit, this goes to the derivative. So the derivative is the slope of the tangent line. Now you have a parametric equation, a parametric curve. I don't know, a general one. I pick a point. I draw the tangent line. Then we ask, what's the slope of the tangent line at this given point? Think. And Sakina. Okay, so we will, should be similar. M is approximately the quotient of the increment. So how the point moves for this parametric curve, it happens when the parameter changes. So this is approximately y. So y in our case is gx gt. I'm sorry. G t, and x is approximately derivative d t. They cancel each other, so we get the so if we have a parametric equation, then the slope will be the quotient of the two derivatives, the y component over the x component. Okay, let's try one. the circle at pi over 6. Find slope of tangent line. Okay, we have a question now. Where do we start? That's the formula. So in this case, what is G? Sine t, all right. So the slope at pi over 6 is G is the sine t derivative over cosine t derivative. So sine t will be cosine t, cosine negative sine t at pi over 6, cosine pi over 6, sine pi over 6. The cosine pi over 6, oh, sorry, cosine is square root 3. Sine, in this we find the slope. If we draw the circle, and the pi over 6 is approximately somewhere over there. Then the tangent line. Okay, so what we found is the slope of this tangent line at pi over 6. Okay, so let's have 5 minutes break and we resume at 55. Okay, so another quantity for this parametric curve is the arc length. How long the curve is. To find the arc length, we will break this into small pieces as we have done before. And each piece, we use this Pythagorean theorem. It's approximately just in our case, the increment, as we have seen before, increment of x is this, increment of y is this. It's approximately if we take a square root, we have a formula. So then the approximation. We have an approximation for the arc length. We break this into small pieces, find approximation for each of them, add together, we have one approximation. And I have done before, if we take a limit, the limit gives us an accurate estimate of the arc length. So taking limit. We get an integral. Okay, so as a confirmation of the formula, we start with a very simple example, the unit circle. Oh, what happened? Okay, we all know the length of the perimeter unit circle. What's that? The length of unit circle. Okay, we all know that. So the length should be 2 pi. Let's see if we get 2 pi with our formula. 0 to pi. F derivative, F is sine t, and F is cosine t. Derivative square. G derivative sine t derivative square. Sine t. A confirmation. Okay. But in many cases, the integral could be complicated. Sometimes we cannot even integrate it. The very simple formula, but we couldn't integrate. Let's try another example. New page. This is new page. Okay, first, what's the curve for this parametric equation? What's the shape of the curve? This one, if we divide x by 3, we get a cosine t. We divide y by 4, we get a sine t. If we square them, we get a cosine t square, sine t square. So this. So something square, add them is 1. So this is an ellipse. Uh-huh. And we have chosen the number very nicely, 3, 4. And what's the arc length? 0 to point. X will be -3 sine t. Where derivative? Derivative 4 cosine t square. 9 sine square t, 16 cosine square t. Okay, let's look at this integral. A very simple integral. Do you agree this is a very simple integral? Looks very simple. However, this is beyond our capacity. We don't have no idea how to integrate this. Sometimes someone will say it's even impossible to integrate this one. So the mathematicians, they have developed a huge theory about this because of the elliptic integrals. Very difficult to integrate, maybe impossible. Elliptic. I have a browser over here. Maybe I can show you. This is. Do I have a browser somewhere? This is elliptic. LPT. Elliptic. If you Google this, the first topic, elliptic integral. So the result, the integral is something like this, as we have just mentioned. So you can see this is very close to what we have seen before. In our case, if we make this 16, we get something like this. So elliptic integrals. Okay, just let you know, a very simple integral sometimes is difficult to integrate. Okay, so this is about the parametric equations. Next, we introduce polar coordinates. Okay, so Kina, have you seen this before? Polar coordinates. So what are the polar coordinates? R and theta. F x r cos theta. Okay. And the other way is x squared plus y squared is r squared tangent theta. Okay, let me check with you. This r, when you learn this polar coordinates, could it be negative? Is that allowed? Or r has to be positive? Could be negative, right? Okay, so this corresponds to two different conventions. Some book give this. Let me use a different color. If we use this convention, the r cannot be negative. If we use this convention, the r is allowed to be negative. It just go to the opposite direction. Let's see some curves. Yes. R was Okay, let's see this curve. R is cosine 2 theta. We can convert this to x and y. So using the depth R, x is R sine theta. So R is 2 cosine theta or sine theta. 2 cosine theta sine theta. If you double angle formula, you get something. But let's guess how the curve will look like. The circle, how do you get that? You plotted it before. Uh-huh. A circle. Uh-huh. Okay. So let's check. If we use this double angle formula, what we can get is Zichen, what's double angle formula cosine for this? 2 cosine square. And this one. Okay, so we can see x cosine 2 theta, y sine 2 theta. This is what you suggested, it will be a circle. The difference is we double the speed. We double speed, so if theta goes from 0 to 2 pi, if theta from 0 to 2 pi, then this curve, so 2 theta, will go from 0 to 4 pi. It is a circle, but we go around it twice. Mhm. Plot it. On R cosine. Did I get a good one? Remove this. Okay. See another one. R is 1 plus sine theta. Okay, so again, you have drawn this before. How to draw this one? Okay, steps. Maybe what would you do first? Okay. Very nice. Okay, so you know what it looks like. So what we do is we graph this function first. Then we graph the polar curve. Graph the function. Theta and R. We graph the function. Then we graph the curve. One, two, 1, 0. So the curve will go from here, grows, raise, 0. Okay, so we go over this quickly. I've seen it before. Okay. Now we will do some calculus about polar curves. Okay, Elisa and Sophia, any questions? Have you drawn this before? Maybe it's Sophia.
Yeah.
Okay, you have. Okay, so I think we are safe to skip this. Polar curves. The first one, let's start with something easy. You have a unit circle. Not a unit, an arbitrary circle of radius a. Wait, no, the area will be pi a square. Agreed? Now if I cut this in half, okay, what's this area?
Divided by 2.
So it will be pi r a square of 2. If I divide by a quarter, it's divided by 4. Now I give an arbitrary angle. Give you this, start here and there, theta. So what is this area?
Times theta over 2 pi. Or no. No.
Mm-hmm.
Yeah. Times theta over 2 pi.
Theta over 2 pi. Okay, so, and here we have the radius a. How does this change? It depends on the radius, right, Sophia?
Yeah.
So we multiply this by a square. Okay, okay. And there's no extra pi. Just a pi theta over 2. Okay, let's check. So I claim this area is a square theta. Now see, if theta is the whole, if we are considering the whole disk, what is theta? So theta will be pi, and the area is a square over 2 pi a square. If theta is pi, half circle, a will be a square over 2 pi. Okay. So this will be the formula we use for a sector of angle theta. And we use this to find the area for polar curves. Let's start with a polar curve and see how we can formulate, give a formula for the polar curve. Okay, so I have a polar curve. R is f theta. Start angle, ending angle. Now I'm interested in finding this area. Okay, what should we do? Using the idea of integration. So if we want to use that idea, we break this a big domain to some smaller ones. We break this into smaller ones. And for each one of them, we approximate the area using this formula. So the approximate area the radius is given by this function. 1/2 Ri square increment. 1/2. So adding these elements together, we have one approximation. The same idea we have when we define the integral. Just this case, we use a geometric element. For each small sector, it's approximately a circular boundary. So we can use an approximation for this area. Agreed? Agreed? Okay. Now, so we have many approximations. We add them together. So this gives us an approximation of the total area. What's next? We have approximation. Where do we go from here? How do we find the exact area? Very simple. What do we do? When we have the approximation, we make this finer and finer, get a better and better approximations. We take a limit, and the limit will be the integral. Taking limit, we have the area from summation to integral. Okay, let's try an example. The example, we know the answer and we want to confirm our results. R is 2 cosine theta. Again, we want to find the area is from 0 okay, so it's a circle of radius 2, radius 1. And we expect the area should be pi, and we check if it's correct using our formula. 0 to pi 1/2 2 cosine theta squared. Is it? Okay, we integrate this will be 0 to pi 2 cosine theta squared. Sophia, how do we integrate this one?
Um,
2 cosine squared.
that is the same as 2 sine. Wait, you can take the 2 and put it on the outside.
Let's try the double angle formula. If we apply double angle formula, what does this give us?
It gives you cosine 2 theta.
Cosine 2 theta. So 1 plus cosine 2 theta. Then we integrate. This will be theta plus 1/2 sine 2 theta 0 to pi. So pi sine is going to be 0 minus 0 plus 0 is pi. So this is our formula to find the area bounded by a polar curve. So the integral from the starting to ending 1/2 of the square. So why do we have a square? Because each piece is approximately a circular sector. We have this area element. That's why we have the square in the formula. Do you agree? Okay. Okay, so the area is very nice. A little bit challenging in this case is the arc length. Again, we have the polar curve. Okay, I have 5 minutes and finish this formula. So as we have seen before, the increment is x in our case, okay, Sakina, what's x? If this is our polar curve, what is x? In polar coordinates, it will be r cosine theta, right? So r cosine. And for this curve, r is f theta. Okay, okay, okay.
Okay.
Okay, so we have this x and y, and we are going to plug this into the formula. It looks very complicated. F theta cosine theta derivative square. F theta sine theta. Whole thing derivative squared. The good thing about this, there are a lot of the trig identity allow us to simplify many of them. So the resulting formula is very nice. F theta. Then we take a square root. The increment will be f theta square. F derivative theta square. So we have the arc length formula. So be very careful about this formula. In the formula is the f square, f derivative square. You compare it with the formula in the regular case. Is A B. Okay. And both of you, Skinner and Zichen. I want to emphasize the difference of this arc length for different parametric equations. This is the general one. It's x derivative square, y derivative square. But if we're in the polar coordinates, it will be f and f derivative. So how do we here have two derivatives, x derivative and y derivative, but now only f and f derivative? The reason is hidden in this step. There are many simplifications in this. This could be quite long, so this gives you 6 terms. 6 terms. If you simplify, you get a very good one. So I will encourage you to expand the square, do the simplification. Then you get this formula, you say, okay, so these two are the same formula but in different situations. Parametric curves and polar curves. Okay, so we'll stop here and we'll continue on Friday. Any questions? Okay. Okay.